Hello everybody and welcome to AJS. I'm really happy to have today with us Isabella. She's a master student. She's doing her master thesis here in the MATLAB group, and today she will talk about a numerical spectral approach to stochastic PDE resolution and asked back with Bayesian Inference. So please, Isabella.
Thank you. So as Pierre anticipated, I am talking about the main topics of my master thesis, and I'm introducing the topic with a review of literature about it and the most used methods to solve stochastic PDE. And then I'm proposing a new approach basing it on last researches on the topic, on the field, which inspire some ideas also with Federico Pichi, Moaad, and Gianluigi about some intrusive way in which we can simulate a PDE system with stochastic components. But first of all, I want to point out the usefulness of this kind of approach. In order to do that, I'm bringing you an example of a very famous PDE system, the Borges equation, used in physics in many areas, such as mass transport, turbulence, etc., etc. What I want to show to you is that changing the initial conditions a little bit, so introducing a stochastic parameter in the system, which in this case is this kind of rumor, this kind of noise, which is uniform, and introduces a uniform noise from 0 to 0.1, so a 10% noise in the system with respect to the deterministic initial conditions. If I do that, what I obtain is that the solution changes very much. What I mean with this? I mean that in this graphic, you can observe the mean solution in the solid line, while these other two lines, the dot ones and the dashed dot one, show to you the bounds of the solution obtained with different values of the stochastic parameter. What I want you to think is that this kind of noise, which would be maybe irrelevant at the first sight, it is very, very relevant in the sense that the transient changes so much. The transition point is very much shifted when a little noise is introduced in the system. This is only an example of how important it is to have a probabilistic knowledge of the solution of a PDE system and not only a deterministic one. Because even in numerical methods, we introduce noise, we introduce errors. So if we want to have a realistic knowledge about the model response, we have to include in the analysis also possible fluctuations around the value of the parameters we want. This is not the only reason we want to understand the stochastic behavior of a system, because having a probability distribution as a solution and not only a deterministic function allow us to do a post-analysis, which could be also interesting. I will explain to you later Bayesian approach, the Bayesian Inference approach, which basically takes the solution, the probabilistic solution of the system as the starting point of a posterior analysis, which will lead us to include in the solution that we are calculating, we are computing, also maybe some observation knowledge, because the Bayesian inference basically works as we have a prior knowledge of the system, which will be our probabilistic solution of the model, and then we have some observations based on real knowledge. We can combine them and have a probabilistic description of the model in a more complete way, which will be much more reliable if we want to have realistic, we want to find realistic conclusions about a system that we want to study or simulate. So This is why stochastic modeling and also applied to uncertainty quantification is very important if we want to perform analyses which are reliable. Going on, I will now explain to you some methods that come in the way when we want to perform stochastic simulation in an optimal way. So the main drawback about stochastic simulation is that if you want to solve a stochastic model rather than a deterministic one, you have to have much more computation. So the cost is higher. What we want to do then is that to introduce some surrogate modeling and lowering the cost, lowering the computation so that we can obtain a reliable solution with a much less cost of time or resources in general. So the first thing that I want to explain to you is the Karhunen-Loeve Expansion. Now I'm in the setting of a given stochastic process which has a finite variance, so a finite second moment. And the Karhunen-Loeve expansion, as you can see in the first line, expands this stochastic process as a summation between a term, a spatial or a time-dependent term, depending on the system, and then some kind of variables, of stochastic variables here, which are introduced in the system and said to have mean equal 0 and to be uncorrelated. So this kind of expansion has been studied so much, and some important results come with it. In particular, this is like a spectrum approach, because these kind of function of spatial functions and this value are respectively the eigenfunctions and the eigenvalues of the covariance matrix of the process. So here is how they can be obtained, solving an eigenvalue problem. And this kind of result brings us the things that we have orthogonal eigenfunctions, because the covariance matrix is positive definite and is symmetric. So we will have decaying of eigenfunctions with a velocity that will depend on the type of covariance function. And an important thing is that this kind of expansions is the optimal expansion, is the optimal one in the sense of mean square error, because it is minimized and the error is orthogonal to the basis of the projection. So it is a very important surrogate modeling for a general stochastic process. Now I want to underline which random variables are there. I've said that these have to be uncorrelated and their mean is 0, because the mean value is then represented by this term here. I want you to understand that in general, for some variables to be uncorrelated doesn't mean they are independent. This is something that coincides in the case of Gaussian distribution, but for general distribution, it is not true. So it could be a problem when we want to approximate not only Gaussian processes, but also processes with different type of characteristics. This is the first limit, if you want, of the Karhunen-Loeve expansion that limits its usefulness in modeling general things. But the second thing is that when we solve the eigenvalue problem, and so we want to infer the eigenfunctions and the eigenvalues, we have to solve a numerical system like that. And you can see that this is something that became much more, the cost arises when the dimensionality is higher, and we have the problem of curse of dimensionality. Going on, I will now explain to you another surrogate model for a stochastic process, which somehow is much more easy to use and has less limitations than this one, and also generalize this approach. This was the first approach that was proposed because we obtain orthogonal eigenfunctions, because it is a spectral approach, because it has some bounds on the error. But all these characteristics, when then generalized by another approach, which is the polynomial expansion, which is a general polynomial expansion method. And now I will talk about it. In particular, in order to talk about it, we have to introduce the concept and the architecture of the Askey scheme. The Askey scheme is an organization of some type of polynomials, of orthogonal polynomials with respect to a given weighting function, which has been made by Askey in the last century. And basically, it is a unified way to express such polynomials using hypergeometric series. Here, I show you the diagram, which is like a tree, if you can see, and goes from up to down. And more and more that you go down with those connections, you can see that the connection represents like a limit. So going up, going from the upper squares to the lower squares, we perform a limit of some parameters of the distribution. In particular, I bring to you an example of the Jacobi polynomials, and not distribution polynomials, of the Jacobi polynomials and their mid one. The Jacobi are these Pn polynomials, and when the alpha parameter goes to infinity, we arrive to the Hermite polynomials. But why are those polynomials important? I've said it because they are orthogonal with respect to a given weighting function. In particular, for example, the Legendre polynomials are orthogonal with respect to the weighting function which is constant to 1. So if you think in a probabilistic way, it is like orthogonal with respect to the uniform distribution. So the Hermite polynomial, on the other hand, are orthogonal for the Gaussian distribution because the weighting function is like that. This is something very important, and it is the basis of the general Polynomial-Chaos expansion. Now, this general Polynomial-Chaos expansion is something like that, if you can see. It is like an approximation of a function depending on, in this case, this parameter could be a spatial one if f is not a random variable but a random process, because the difference between random variable and random process is that the random process is like a collection of random variables. So if you insert in the model also the spatial dimension, this kind of coefficient became spatial and not only numbers, as in this case, but it is only an introductory example. These functions, depending on the random variables, on the random variable z, are the polynomials of the Askey scheme. And the kind of polynomials that we're choosing depend on the distribution associated with z. So if z is a Gaussian distribution, the polynomials will be Hermite polynomials. If z is a uniform distribution, the polynomials will be Legendre, and etc., etc. This is like some kind of generalization of the expansion we've seen before, because the way the computations that leads us to compute the coefficients is very different, because before we solved a eigenvalue problem, while here we have just the polynomials that are ready and we have just to compute the coefficients. But in the Gaussian case, those kind of expressions are equivalent. So the general Polynomial-Chaos is like a generalization of the previous one. Here it is, we can see that the computation of these coefficients is like the projection of the function on the general polynomial, the Askey scheme polynomials chosen. And here I remind to you that these expansions are important because the error is bounded, the error is known, and in particular the error is orthogonal to the projection basis. And this result is a numerical result is very known in general interpolation, in general numerical approximation schemes. Now, another difference between the previous expansion and this one is that, if you remember, the previous expansion has needed many random variables, many uncorrelated random variables. This one, in general, can perform an approximation of a random process only using Z, which is called the germ with a given distribution, the germ of the expansion with a given distribution. So a random variable with a single random variable with a given distribution. But if you think on stochastic PDE, for example, you could want to express the random components of the system not only as a parameter, not only as an initial condition, but as a parameter and an initial condition and some boundary conditions. So you could have an ensemble of conditions that are of random conditions that you want to include in the model to see how the solution performs. You can do that with a multivariate general Polynomial-Chaos expansion. So you could insert various random variables inside the system and want to model the solution basing on all of them. Here comes the orthogonality of the polynomials and the independence of the random variables that you are considering, the random variables or the random processes. In fact, if you assume that the stochastic parameters, the stochastic initial conditions that you are considering in the systems are independent, which is something that you may want, because an initial condition is like independent on a parameter of the same system. You want them to perform independently. So if you have this assumption basing on the orthogonality of the polynomial, you can see here that the density function is like the product of all the density functions. And this kind of result brings us to the simple result that the polynomials of the multivariate expansion are like the product of the polynomials of the univariate expansions. Here, like you have a multi-index, and for a multi-index that is the sum of the indices of the univariate random variables, you can perform an expansion given that the multi-index is minor or equal than a certain n that you may want, which n was the degree of the polynomials before. Now the degree of the polynomials, you have to take into account that it is a product between multiple polynomials with individual degrees. So it's like, that's why you have the multi-index. Here, like, is the dimensionality of the space when where n is the degree of the polynomial and d is the number of the random variables, and that's kind of how you perform a general Polynomial-Chaos expansion with multiple random variables. Another reason why general Polynomial-Chaos expansion can be very useful and appealing, if you want, is that the statistic moments of the random process are very clearly represented in the general Polynomial-Chaos expansion. In fact, given also the orthogonality of the polynomials, you can see that wanting to extract the mean, for example, the result of this operation is just the first term, the first coefficient of the expansion. So it is very easy to obtain it once you have the expansion. Also, second moment, third moment are very easy to extract because you only have to sum and perform the product between the coefficients that you have when you have the expansion. So no additional computation is needed to extract a statistic analysis of the solution, which is very important because you don't have to perform the integral, for example. So there are not additional quadratures to be made. Now, those surrogate modeling, those expansion of a stochastic process can also be introduced inside a very famous discretization method, which is the finite element method, which I assume you're familiar with. And what it is done is to introduce the expansion of the stochastic process inside the model. In which way? First, you have, I assume we have a stochastic parameter that we want to include. This stochastic parameter is modeled as the first expansions that we have seen, because it is like we want it to have a general expansion, so we don't want the solutions to depend. The question is why we don't use the general polynomial expansion also for this parameter, because basically we don't want the solutions to be so dependent to the form that we give to this parameter, because the probability distribution of the solution could be much different from the parameter one. So if we have a Gaussian parameter or a beta parameter, it doesn't mean that the solution of the PDE system will be Gaussian, beta, etc., etc. So we want them to be separated. We want to approximate the parameter with Karhunen-Loeve expansion, while we are going to give the form of Polynomial-Chaos expansion to the solution, having some kind of basis of the Askey scheme, the polynomial Askey scheme basis. So we introduce these summations in the system, and what we are going to do next is to perform finite element approximation as we know it. If you have a spatial domain, for example, so we approximate the spatial domain as with a series of Lagrange polynomials, for example. So we perform triangulation, etc., etc. And then we want to integrate both parts of the equation after multiplying with the Lagrange basis. For example, this is the standard finite element method. We are going to express then these kinds of coefficients, spatial coefficients, as a series, a summation, so as an expansion depending on these, which are the Lagrange polynomials. And so we can do the spatial finite element method as we know it. We have now to perform another step, because we are in a stochastic setting, and we have also to perform the same thing, but in the state space of the random variable. So we are going to multiply both parts of the equation by the Askey scheme polynomials, and we are going to perform the integration. The integration is, in some cases, can be facilitated because the polynomials are orthogonal. So you know some results. That's kind of the idea behind stochastic finite element method. You can see that it's very similar. The concepts are the same of the finite element method, but the enhancement is that you perform a second step of integration, if you can, on the state space of the random variable that you are considering. Okay, now I want to point out that intrusive ways on collecting and finding the coefficients of the general Polynomial-Chaos expansion are not the only ones. There are also non-intrusive approaches, which are called stochastic allocation methods, and the way in which they operate is very intuitive. So you have the general polynomial expansion that we have seen before. You put it into the PDE system, and you want to extract the coefficients of the solution. What you do is that you perform a sort of sampling in the space of the random variable. Then you solve the deterministic system for those kind of random variables, and then you perform the interpolation basing on the results that you get, and you find the coefficients. What you can see and think is that in this kind of non-intrusive approaches, the traditional problems of interpolation comes out, such as unknown fixed error bound outside for not sampling points, and the curse of dimensionality when we want to include many random variables in the model. Here I point out that there have been studies on surrogate collocation methods which try to reduce the curse of dimensionality. As you can see in this picture on the left graphic, we see a point collocation very sparse, while on the right one it is much more sparse, and there are results that confirm that in multidimensional cases this kind of grid does not perform badly. So it is like in stochastic collocation methods, there are also some researches that try to reduce the computational cost, but the general drawbacks are the same. The general resources cost and the non-fixed error, that unless you have on the intrusive with the intrusive approach, even if could be much more model related and has also its problems. But if you have your model and you want to infer the knowledge of the solution, the intrusive approach could have also so many benefits, unless the non-intrusive one. Now we have arrived to the announcement of all these probabilistic architecture to have a solution, a probabilistic solution of a stochastic partial differential equations, which is the possibility to infer a posterior knowledge of the system. Here I put like a little example for those of you who are not familiar with Bayesian inference, but basically what I have is a prior knowledge of the system, is a likelihood, which is like the distribution of the observations, so external knowledge, and then you have a way to combine these two knowledge in a posterior knowledge. This is like a very, as I pointed out in the introduction, a very powerful way in having a comprehensive solution and knowledge of the system, and could bring also some advantages in case of unknowns. What I mean that sometimes have a model. Okay, that sometimes when you have a model, you are not sure which parameter, the range of the parameters the model has. You're not sure which distribution you want to give them, where is the mean of the parameter. You're not sure. You have to infer those informations as posterior information, posterior from the observation of the real system. So this is like also a very useful tool to find like the correct values, the correct distribution of parameters that you don't know in advance. So you have some hypothesis, and it is the prior distribution. Then you have the real observations, and you combine them. That's what I mean with the Bayesian inference applies to hyperparameters learning, for example. Hyperparameters are like some parameters related to the model, some parameters which the solution of the models depends on. And that could be like some parameters of the distribution of the diffusion parameter that you are considering, some parameters related to the initial conditions, to the shape of the domain. You can parameterize the shape of the domain and then inferring the parameters of the parameterization shape from a posterior distribution, etc., etc. So it is a very powerful tool based on the Bayesian formula, which is something like that, when you have the likelihood, the prior, and then the posterior. This is like a normalization factor. And it is important. I want to now bring the Bayesian inference concept inside the architecture of solving a PDE, so having a discretized solution of the PDE. We can see that in this statistic model, Z is like the solution of the system, while E is the randomic error that we introduce. Y are the observations. So this is the relation. Then I expand Z in PU, which is a projection of the solution of the finite element method, a projection inside the space of the observations. And then D, which is the error that I consider on the finite element method solution. This is like a statistic model which includes inside it all the possible noises, errors that we can have when we discretize a system, when we discretize a solution. From this statistic model, we can infer this likelihood function. So the density probability of Y given the solution U. In a general polynomial-Chaos expansion setting, this is very easy because you can write it analytically. Because you have the expansion of U, you can write PU as an expansion itself of some general Askey polynomials and coefficients. And then you can extract the distribution of Y given the distribution of U, which is the likelihood function here. Then you perform the Bayesian inference and you can find the probability, the posterior probability that you want, which in the case of hyperparameters learning is this kind of probability. So the probability to have a certain value of the hyperparameters given the observations. This setting of Bayesian inference can be used in so many cases given the probability of the solution, because what maybe I have not said enough is that this prior, the probability distribution of the solution is what we obtain from the solution of the partial differential equation with the stochastic Galerkin method. So it is something that we have. Actually, we have to marginalize that function because we have it, because we have to marginalize with the distribution of the stochastic parameters of the stochastic terms that we have introduced in the stochastic model, but we can infer it. So these we have from the stochastic finite element method. These we have from the statistic method, and then we can infer the posterior knowledge of the parameters, for example. But we can infer also the posterior knowledge of so many other things, such as, let's say we have a difficult system to solve, and we don't really know if some grid is correct, or if some other grids are much better than the previous one. So we have different models. How can we classify those models? How we can say which are better? We can say by having a posterior distribution which tells us what is the probability given the observation that the model 1 or the model 2 is correct. Basically, this is the message. You can also extract the bias factor if you want to compare those kind of models. And then you have like a comparison that has been made. In the setting of general polynomial-Chaos, as I pointed out before, it is very easy because you have an expansion that you can very easily manipulate and extract basically what you want. Now, some relevant applications of the general methods, of the general procedure that I've shown to you. What we are concentrated on right now is like finding some ways to apply those settings to bifurcation systems around a bifurcation point. This is the example of the Poaad effect for instance, when you can see that here is the spatial domain, and what is represented here is like the variance extracted from the solution. This was a simulation performed by Monte Carlo approach, but the results with intrusive, non-intrusive models are basically the same, not in terms of accuracy, but in terms of aim. I want to show now the aim of all this work, not the results themselves, because they're not conclude. The work is not concluded right now, but the aim is to extract statistic information, which can be useful in bifurcation settings in many ways. Here, for example, you can see that the variance is peaked here, and so maybe you can know, oh well, maybe here there is a bifurcation going on because the solution is not, the variance of the solution is very high compared to the others point. In fact, if you're going to study the solution on this point, we will find a bifurcation diagram like that. And so it is like a very important information that we could bring out of the system, considering a stochastic parameter inside it. Even when the stochastic parameter is in a very critical point, such as the bifurcation point, and so you have very interesting and qualitatively different behaviors around it. So here it is the relevant application on which we are working on right now. And that's basically all. Various ideas about how to include the stochastic simulation inside the bifurcation analysis are explored, but maybe I will present another time then. And so basically, 40 minutes. Okay, perfect. Perfect. And that's all. These are some references if you want, the main one, some books and some recent articles. And thank you for the attention.
Thank you, Isabella, for the nice talk. Now it's question time. So if you want to do some questions also online, you can write it on the chat, or you can unmute yourself and ask them. Maybe I have one. Which library have you used for the simulation?
For the simulation, I used ChaosPy, which is a Python implementation of general Polynomial-Chaos, which is very useful for exploration. See, maybe I will implement something also by myself. That's what I'm working on right now. But general Polynomial-Chaos and also Phoenix for the finite element setting.
And for something about the geometrical parameterization,
yeah.
Have you tried something that works in the project?
There is the idea, but I've not tried something. I've not tried something such right now.
Okay,
but it is not done. But maybe it will be done for the end, for the end of the thesis. So it is something that we are thinking about, because it is very important and interesting to understand how the solution changes in different domains. So also enlarging or restricting the circle, for example, a circular domain is like something.
It's more a curiosity. When you talk about Bayesian Inference approach, so in that sense, you also lose, I think, the error bound on the solution that you use, because you cannot compute analytically the determinant, the denominator of the stereo, right?
Yes,
And we use
quadrature, yes. But at that point, I would say it is not the aim to have an error bound, because you have the error bound when you solve the system, and then you include external knowledge. So it is something forward step. I would say that. Data, yeah, because the Bayesian inference is useful, for example, when you don't know how a parameter is made, no? So then you have some hypothesis about them, you solve the system with a good error bound, and then you take the external knowledge, which is separated, and you include, and you assume that what you get is a comprehensive thing of the first and the second.
So can you go back on the one shot plot of that? This
We can effect here.
So well, so basically, given for example, let's say this PDE, you, I mean, and for example, given for example, let's say the velocity, you want to apply, let's say, the Bayesian theory to this point.
Sorry, I have not understood.
Given this problem,
See, yeah.
so you want to apply, for example, let's say the Bayesian
The Bayesian effect again.
on student, like for example, the velocity.
Okay. Like the Bayesian things is not the focus of this example. I've not shown in this example how I can perform Bayesian inference. Here I've shown how stochastic simulation is useful to identify like a portion of the space where the bifurcation may be occurring. Did I answer? Because then you're asking me whether or not Bayesian inference is done that. No, in this case, it is not done, or maybe it is not what the example is showing.
Is it possible to apply, let's say, the Bayesian effect for this kind of problem?
Yes, because you have, for example, if you could resolve this problem with general Polynomial-Chaos, then if you don't have any idea about the parameter here, and maybe you have a prior distribution which is picked in 0, but then you have some observations like that. Maybe you have a posterior inference on the parameter, which is shifted versus the point that you actually are interested in. Even if you didn't know the, like, okay, assume that this kind of parameter is not known in advance. So you don't know where the bifurcation is. You assume that it is around this kind. So you solve the system like that. But then you have some observations, because you have run the simulations for some parameters around also this kind of area. So you have this observation that goes in that way. Then you combine those knowledge, and maybe you are going to understand as a posterior knowledge that the bifurcation parameter is not in this area, but is shifted. Something like that. Yes. Could be.